Hello class, and welcome to part 2 of the section Cements. Today we're going to be looking at Portland cement and also certain blends of Portland cement with other kinds of cement. Last lecture we talked about lime and we talked about gypsum. They were both non-hydraulic cements. Portland cement is a lot more common than either. It's a hydraulic cement, meaning it reacts with water and part of the water molecule forms the final molecule that is in the hardened cement. And generally hydraulic cements are a lot stronger than non-hydraulic cements. That's a generalization, but Portland cement, it is a very strong cement, and that's why we use Portland cement in just about most concretes we use today. They will be using Portland cement or a variation of Portland cement. So what is Portland cement? Well, it is by far the most common cement we use in civil engineering. If you buy a bag of cement from any hardware shop, if it doesn't have the term Portland cement on it, if it doesn't say lime or it doesn't say what kind of cement it is, it's probably Portland cement. Now, if you look at that bag that we can see in the top right hand corner, it says Portland cement type 1/2. We're going to be talking about the different types of Portland cement later. But this is a mixture of type 1 and type 2 Portland cement. You have about 5 different types of Portland cement, and we'll be talking about what causes that later. What are the different types and their variations? But Portland cement came very late on. It was developed by John Aspen of Leeds. It was invented in Leeds in the centre of the Midlands of England. It wasn't invented in Portland, and it came about in 1824 BC. Now, with Portland cement, you've got to know that the reason it's called Portland cement is that it's got a very light colour to it. It's got this light grey colour that we now associate with concrete. Before Portland cement came along, most concretes used lime cement, and they were a lot darker in colour. They were much darker greys. Now, when John Aspen invented Portland cement, he noticed that the colour was very light, a light grey colour, and he said it's very like the stones that are on the beaches of the Isle of Portland. So the Isle of Portland is a small headland in the south of England where lots of people go on holiday. It's basically a holiday destination in England. And John Aspen used to go to Portland on his family holidays, and he said, you know what, this cement that I've created, it's very much like the stones on the Portland beaches. So you can see a picture of Portland down there, and you can see all these very light coloured stones on the beach. And that's what Portland cement resembled. But the reason it became so popular very quickly, and today, as I said before, with the exception of maybe a little bit of plastering and brick mortar, Portland cement is used in 99% of all concretes in civil engineering. And the big reason is it's very strong. It's far stronger than any other cement. And I'll be talking to you about why that is in a little while. So with Portland cement, you've got to realize that actually it's a little bit of a mixture of two different elements in ingredients. One ingredient is lime, which comes from limestone. Remember, we have calcium oxide. And then it's also a mixture of silicas and aluminas, meaning they're sort of oxides which are combined with silica or aluminium, and that comes from sand or clay. Now in Kurdistan we get the silica or alumina from alluvial sands. So sands around the banks of the Zab rivers, that's where we get that ingredient from. And what happens is you mix those two ingredients together, the crushed limestone and the alluvial sands, and you can build Portland cement out of it. Now the mix proportion is about 60% calcium oxide, 20% silicates or silicas, and 5% aluminas. And you may realize there that where does the other 15% come from? Well, that's actually just impurities. But that's basically what we will be proportioning. So roughly you will be putting in about 60% limestone and then about 40% sand or clay. Now you crush it and you heat it up to 1500 degrees Celsius. Note here that that's a lot hotter than what you need to make lime from limestone. For lime, all you needed to heat it to was 900 degrees Celsius. And so it requires a lot more heat and energy to make Portland cement. And that's why, one of the three reasons why environmentalists are eager for us to design infrastructure that uses lime more than Portland cement. It uses less energy. But it's an endothermic reaction, meaning you've got to add heat to it. And basically, when you have those ingredients, they will make lots of different products, but the three main products that it will make in terms of chemistry are tricalcium silicate, dicalcium silicate, and tricalcium aluminate. So in this case, you can see that the calciums are combining with a silicate or an aluminate. Now, you can see the chemical formula for those right there: CaO SiO2 or 2CaO SiO2. I'll have to say that with civil engineering, us civil engineers, we tend to be a bit lazy and we don't write out the full chemical formula. Tricalcium silicate, what we call that is normally C3S. Now obviously the C is not carbon, we're referring to calcium. And the S is not sulfur, we're referring to silicate. Dicalcium silicate, in turn, we call that C2S, and tricalcium aluminate we call C3A. Now, that is the product inside Portland cement. When you buy a bag of Portland cement, those are the three main molecules inside that powder. Now, there's a lot of other molecules as well. You're never going to get a pure Portland cement which has three of those, but those are the main ones. So with Portland cement, this is what it looks like. If we were able to look at a molecule under a microscope, the tricalcium silicate will look like that molecule on the left. You've got the silicate in the center and you've got three calcium oxides surrounding it. Now, and it's sort of in the shape of a pyramid. Now, it should be clear to you that the calcium oxides, you've got an oxygen there which has a very strong negative charge. That means it will combine with water very quickly because water on one side of it has a positive charge. And the same could be said for tricalcium aluminate. You can see there that you've got three calcium oxides surrounding an aluminate. Now, what happens when Portland cement reacts with water? Well, the calcium charges, which are very positive, they combine with the water. And so you end up forming calcium silicate hydrates or calcium aluminate hydrates. That's what happens when the cement reacts with water and it dries. And they're very strong bonds. The water stays as part of the solid, meaning that the water doesn't all evaporate. The water, meaning namely the hydrate, the hydrogen atom or the hydroxide atom molecule, they will be part of the final product. So it's a hydraulic cement. Now that's just a very simplified formula I'm showing you there, but let's look at it in a little bit more detail with the next slide. So let's look at the top reaction here. We've got a tricalcium silicate, and that's the simplified formula there. We've got C3S. It's not carbon, it's not sulfur. It's 3 calciums alongside a silicate. And it reacts with water. And again, we're not writing out the water reaction there. We're just H2O. We're just writing the H because that's the important part. That's going to form CSH, which is basically a hydrated calcium silicate. And then it will also have a calcium hydroxide, CH. Now the calcium hydroxide, you should know, that's a gas. That's going to evaporate. It's going to leave the concrete or the cement. That's why concrete is never completely dense. There's always voids inside the concrete. We'll cover that later. Dicalcium silicate, again, that combines with water and it creates the same product. It creates a hydrated calcium silicate, and it has a little bit of calcium hydroxide gas bubbling off it. Now the tricalcium aluminate is a little bit different. You can see that one tricalcium aluminate combines with 26 water molecules and also calcium sulfate hydrate. So that's the calcium sulfate hydrate. That's in a very small portion. That's inside the Portland cement too. Remember how I said Portland cement has other molecules inside it too? There's also a sulfate element to it as well. That's going to form a molecule which we call entringite. It's basically a combination of calcium, alumina, silica, and hydrates. That in turn will react with more tricalcium aluminate, and that's going to form a hydrated calcium aluminate, or calcium aluminate hydroxide is another term. That's C4ASH12 at the bottom. Now, one thing you need to know here is that the tricalcium silicate and the dicalcium silicate, those are one-step reactions. The tricalcium silicate, tricalcium aluminate, that's a two-step reaction. It goes first to the entringite and then it reacts again and it forms the final product. That should tell you that if there is more tricalcium aluminate than calcium silicates in the Portland cement, the reaction is going to be slower. It's going to go solid and strong slower if there's more aluminate in it. Now, I want to reassure you of something. You don't need to understand these. You need to understand how these formulas work, roughly, these chemical reactions. But I can tell you that I do not know much about these chemical reactions, and so I don't expect you to either. This is really just to show you that basically these Portland cement molecules, they react with water, and what you need to understand is that water is part of the final solid strong cement bond. It doesn't evaporate entirely. Therefore, it's a hydraulic reaction. That's what you need to understand. So don't be afraid if chemistry is not your cup of tea. It's not mine either. I'm not trying to teach you to be a professional chemist. I'm trying to teach you to be a professional engineer. What you need to know is really that the final product, calcium silica hydrates, calcium alumina sulfate hydrates, they're really strong. They're very strong, and that's why Portland cement is a very strong cement. Now, there is something that I need to tell you here. This reaction, all of these reactions, they're just part of many different reactions that are taking place. This is just a sample. When Portland cement reacts with water, there's actually around 200 or 300 different reactions taking place, all of them creating these hydrates, which are very strong chemical bonds. But the three main ones are those three reactions that you can see there. I'm not going to go through the 200, 300 reactions. You don't need to know that. I don't want to teach it. You don't want to learn it. The other thing you need to know, though, is that these reactions are not only happening when the concrete is drying. So you have wet concrete, which is a mixture of aggregate, Portland cement and water, and then it dries and it goes solid. Well, these reactions, even after the concrete has dried and gone solid, these reactions will keep on happening. They will actually keep on happening for many days. Now, that's why it's very important that you do curing, meaning that you keep the concrete wet so that water is still available for the tricalcium silicates, dicalcium silicates, and tricalcium aluminates can react with it. And it's also the reason why concrete actually gets stronger with age. We will talk more about curing later when we go into an introduction on concrete. But remember, what you need, these reactions, it's not just about the cement going from liquid or paste to solid. It's also from going solid, weak solid, to strong solid, because there's still water molecules inside the solid cement which will keep on reacting with the elements of Portland cement for a long time, several days, in fact, even months. So we'll talk about curing and how you ensure that those reactions can keep happening so you can get a really strong concrete later. But how do they make Portland cement? Well, remember what I said. It's basically the two main ingredients are lime from limestone and silicas and aluminas, which come from sand or clay. So follow me here. First off, with number one, they are collecting limestone from the quarry. You can see they're digging up limestone. They're also digging up sand and clay, maybe at a different quarry, maybe at the same quarry. Now they will dump that limestone into a crusher, and you can see there in the top line it's going through two different crushers. It's crushing up the limestone into a very fine powder, and then it's going to a mixer which mixes the limestone with clay and or sand. Now remember what I said, that the proportion needs to be about 60% limestone and about 40% sand and clay, depending on what kind of Portland cement you're trying to produce and the quality of sand and clay you're using. And so they will prepare that. They will mix it all together. They will grind it to make it even smaller particles. Now, the reason they want to make it small particles is because that improves the reaction rate. It means you have a higher surface area, so it's going to react faster. And then what they do is they basically mix it all together. They also put it through a preheat tower there to make sure that it's well mixed. And then they will be putting it through a kiln. Now that kiln, that oven, is going to heat it to 1500 degrees Celsius. It makes it really hot. And what happens is the lime from the limestone reacts with the silica and alumina from the sand and the clay, and they form tricalcium silicates, dicalcium silicates, and tricalcium aluminates. Those three principal molecules that you find inside Portland cement. Now, when it comes out of the kiln, it's actually going to be clinker. It's going to come out in the form of lots of pebbles, quite large pebbles at times. So you've then got to cool it, and then you've got to crush it up again. You've got to make it into a fine powder. But before you make it into a fine powder, you actually add gypsum. And gypsum is usually about 5% of Portland cement. Why would you add gypsum? Do you remember we learnt about gypsum in the last lecture, and we said that it's white, it's weak, and it's attractive, like Mr. Allen? Why would you want to add a cement which is weak when you're trying to make a strong cement? Well, the reason for that is, if you remember what I said, gypsum has a very slow hydration reaction. It reacts with water slowly. Now, Portland cement reacts very quickly with water. You need to add gypsum to the Portland cement in order that it's usable. Otherwise, it will dry far too quickly, and you won't be able to use it to make concrete. The moment you mix it with water, 5 minutes later it will be going hard and solid, and you don't want that. You want to have time that you can mix it and then pour it into your driveway foundation or your road foundation or your concrete column block, and to mix it with aggregates so you can make concrete. So gypsum is mixed in with the Portland cement. Now that's present in all Portland cement. You have it in, when you buy a bag of Portland cement, you don't need to then add gypsum to it. It's already in there. All Portland cement will have a portion of gypsum, and it's to slow down the reaction rate, the hydration reaction. And it's mixed up. It's ground up, so it's a fine powder, and then it's put in bags, and then it goes on the truck, and it can be taken to the hardware store and to builder supply stores, and it's ready to be used to make into concrete wherever. That's how they make Portland cement. So what you need to know there is how and why they mix sand and clay with limestone. And also you need to understand why they add gypsum to the Portland cement. Why is that a portion of the Portland cement? So once you have the Portland cement, you have a cement which has some very good properties. The great thing about Portland cement is it's really strong, and it's strong in compression when it's being pushed together. That's why concrete makes, when it's made with Portland cement, it makes a great foundation for houses. It makes a great material for building columns for high rises, or piers for bridge piers or dams. The very high compressive strength makes it the product to use, the material to use. And that's why they use Portland cement for most concretes. Now keep in mind it's very fast setting, meaning it's a very fast hydration reaction. Those chemical reactions I showed you before, they will start occurring almost immediately, meaning that it won't take long for the concrete, if it's made from Portland cement, to begin to go solid. So this is something that you need to be aware of. If you make a concrete and it's very runny, within 1 hour it could be quite thick like a honey, because it's basically drying out. The water is reacting with the Portland cement, and that's why you need gypsum in the Portland cement. It slows it down, otherwise it would just be useless. You wouldn't be able to use it for anything. Now, there are some negatives with Portland cement. It can react with sulfates. Now, where do you find sulfates? Well, in some aggregates there are high levels of sulfates. So if you have a concrete which is a mixture of Portland cement and aggregate, when that concrete is dry and solid, over time, and I'm talking in a period of years, sulfates from the aggregate can react with the Portland cement and form what's called sulfite crystals, and that will cause the concrete to crack. And we'll talk about that briefly in introduction to concrete in the next section. But the good thing is, for Kurdistan, you don't need to worry about that. Why? Because all of the aggregate that you have in Kurdistan, it's not volcanic aggregate. You don't have any volcanoes in Kurdistan. It is volcanic aggregates, things like basalt and dolomite and andesite, that has a lot of mineral which is sulfate in it. So this is a problem in New Zealand, where we have aggregate that has very high sulfate content because we have a lot of volcanic aggregate. When we're using that to make concrete, we need to be aware that over the years the aggregate could react with the Portland cement and it could start cracking because it starts forming these big crystals inside the concrete, and it weakens the concrete. So we have ways around that. We use a special kind of Portland cement, or we use an admixture which basically stops that reaction. You don't need to worry about that so much here in Kurdistan, but if any of you ever find yourself working overseas as civil engineers, as I have done, then you need to remember that if you go to a place with volcanic aggregate, you've got to remember that the Portland cement may react with it over time. Now, Portland cement has a very moderate heat of hydration. It's not too hot. Remember what I said about how lime, there's a lot of heat that comes off it while it's hydrating, so much so that it can burn fingers off. Portland cement, it's not too bad. It's a lot safer to use than lime. However, it's still moderate. You can still burn yourself with Portland cement, and that's why you've still got to wear gloves when using Portland cement. The other thing that makes Portland cement a little bit problematic is if you look at the final products, the calcium silicate hydrates and calcium aluminate hydrates, they've got very high surface areas. If you were going to draw those molecules, they're sort of a star shape or pyramid shape. Now, that high surface area means that the surface of your dry concrete is going to be, at a molecular level, it's not going to be very smooth. There's going to be little ruts inside it, and it's going to have little dimples inside it. Now, if you were building a concrete footpath, let's say, in a place where it's cold, such as Choman, what will happen is when it rains, water will puddle and sit on that concrete footpath, and then it will freeze, and it will thaw, and it will freeze again and thaw. Now, with concrete, with water, when it freezes, it actually expands, it grows in volume, and when it thaws, meaning it melts and goes back to liquid, it gets smaller in volume. That is going to push the small gaps in between the Portland cement that's dry. It's going to open and close them, and it's going to lead to lots of small micro cracks called freeze-thaw cracks in the concrete. We'll talk more about that when we go into Intro to Concrete. But this is one of the issues in places where it's cold, where water outside is often freezing and then melting, freezing and melting. Places like Shoresh and Choman. It's not such a big deal for concrete in Mosul or Baghdad. So remember what I said about Portland cement, how there's a lot of different types of Portland cement, and if you buy a bag of Portland cement, it will usually say Portland cement or GC, meaning general cement, on the bag. But there will also be a name where it says type 1 or type 2 on the bag, or another type. Well, that's because Portland cement varies depending on what you're using. So type 1 Portland cement is often called GP, or General Portland Cement, or GC, General Cement. And the composition of it is roughly around 70% dicalcium silicate and 20% tricalcium silicate. So most of the cement is basically where there's only 2 calciums to every silicate. And the last 10%, well, that's a mixture of gypsum, a small amount of aluminate, tricalcium aluminate, but a very small amount, and also impurities in the mixture. Now, that's the most common cement. It's also the one that's used usually for normal concretes, grouts and mortars. For brick mortars, although often they'll use lime for brick mortars. Now, type 1A as another example, that's the same as type 1, but there's a little bit of air entrainer in the admixture. So an air entrainer is basically a soap. It's a small amount of soap that's added inside the concrete, and what that does is it creates lots of millions of tiny little bubbles inside the concrete. Now, that will make the concrete weaker, but what it will do is it will make it less susceptible to freeze-thaw cracking. And I can try to show this to you on the whiteboard when we have our tutorial, if you like. But basically, there's little bubbles or air bubbles inside the concrete, which gives water that is sitting on the surface room to expand and then shrink as it freezes and it melts. And that stops it from cracking. And so type 1A cement is sometimes used in places like Choman and Shoresh, where there's a lot of freezing and thawing in the weather there. Now, type 2 Portland cement is very similar to type 1 Portland cement, but it also contains about 8% of tricalcium aluminate. So why would we want more tricalcium aluminate in the cement? Well, one of the good things about aluminate is that it's more resistant to sulfate reactions. So remember what I said, if your aggregate has high amounts of sulfate in it, the concrete will crack through the years. So this is a way that we can resist that. That's why in New Zealand, if we're using a volcanic aggregate, we generally use type 2 Portland cement. The other good thing about type 2 with tricalcium aluminate in it is that if you remember, the reaction that takes place for aluminate is 2 steps. It's not one step. It goes first to entringite, and then the entringite reacts with water, and then it forms the calcium aluminate hydrate, the final product. Now that does 2 things. First off, it means that the reaction is slower. The hydration reaction is slower, which means it doesn't dry as fast, which is a good thing if you need lots of time to place your concrete and mix it. But the other thing is that the heat of hydration, meaning the heat that comes off the reaction as the Portland cement is reacting with water, heat is coming off, similar to lime. The heat of hydration is lower. Well, why do we care about it having a lower heat of hydration? Well, the good thing about having a lower heat of hydration has to do with thermal gradient cracking. Again, we'll talk more about that when we come to concrete. I'm sorry that I'm telling you a few things which will probably only make sense in another lecture or two. But basically, if I can just explain it briefly here, if you're building a really large body of concrete, and I'm talking something like a big dam, then and you pour concrete into your mold to build this dam, that concrete is going to have Portland cement reacting with water, and as it's drying and as it's reacting, it's going to let off heat. Now, the concrete on the surface, the heat can escape. It can go into the atmosphere. But the concrete in the center of the infrastructure, in the center of the structure, that's going to stay hot. And what's going to happen is you're going to have one part of the concrete which is hot and the other part which is cold. And that can lead to a thermal gradient where because of dispersion, heat will want to go where the concrete is cold, and it will create a crack called a thermal gradient crack. And that's a big problem. You don't want cracks forming in a dam. Type 3 is the same as type 2, but there's even more C3A involved. Now, there's a small error there. It says sets very quickly. It doesn't. It actually is a slower setting speed. And then type 4, there's even more tricalcium silicate in it. Now this, like the tricalcium aluminate, it will lower the heat of hydration, but it doesn't have the sulfate resistance that tricalcium aluminate has. So normally we would not care about type 2 or type 3 in Kurdistan because we don't care about sulfate resistance because we don't have volcanic aggregates. So we will normally be using type 1, type 1A, or maybe type 4. There's also type 5 and type 6 and type 7 Portland cement. This is enough for what you need to know for this course. You can read about the different properties of Portland cement in your own time, but this is just a brief summary. So now I want to talk to you about Portland blends or Portland cement blends. What's that? Well, that's basically Portland cement which is being mixed with another kind of cement. And the first one I want to talk to you about is called Portland pozzolan cement. Now, What's pozzolan? You've probably never heard that term before. I certainly had never heard of it until I started studying concrete. Well, pozzolan is basically ash from a volcano. Now, ash from a volcano, it's got very high silica and alumina content in it. Now, pozzolan in and of itself is not a very good cement. If you were to mix volcano ash with water, it's not really going to dry and form a strong cement bond. It does a little bit, but it's not very strong. However, if you mix pozzolan with Portland, what happens is the pozzolan, the silica and aluminas in the pozzolan, they will react with the Portland cement, the tricalcium silicates, dicalcium silicates, and tricalcium aluminates. They will react with the silica and alumina from the pozzolan. That molecule in turn will then react with the water, and then it forms a new chemical bond, and it's very strong. So generally, Portland pozzolan blends, or most Portland cement blends, have very high strength, much stronger than regular Portland cement. So we would use this for concretes that require very high strength. So sometimes some of the high rises that you see around the world, and I mean very big high rises, I'm talking about Burj Khalifa type high rises, they will often have pozzolan mixed in with the Portland cement to create a very strong chemical bond. It can be up to twice as strong as just regular Portland cement. The other advantage of Portland pozzolan cement is it's got very low shrinkage. What do I mean by shrinkage? Well, what happens with regular Portland cement is those molecules in the Portland cement, the tricalcium silicate, the dicalcium silicate, and tricalcium aluminate, they react with water molecules and they form new molecules together, calcium silicate aluminates, for example. What you need to understand is that the product, the final chemical element, the molecule, is a smaller volume than the volume of the reactants, the water molecules and the Portland cement molecules. And that it's just ever so slightly smaller, but it's roughly around 1 to 2% smaller in overall volume. Now, you may not see this, but concrete, when it dries and as it reacts and goes harder, it actually shrinks. It shrinks by a very small amount. It shrinks by about 1% in size. Now, that's not a big deal if you're making a concrete block, a concrete brick, for example. But it's a real big problem if you're building a dam. And if the dam is 100 meters long and it shrinks by 1%, it's going to shrink by 1 meter. Suddenly you're going to have big gaps that the water will get around the dam in. And it won't just shrink at the ends, it's going to shrink throughout the concrete, which means you're going to have these big cracks forming in the concrete. You don't want cracks in your dam. Water will get through the cracks. So pozzolan, Portland cement, has much lower shrinkage. The final product is much larger, and so the concrete doesn't shrink as it reacts during the hydration reaction. So it's good for large projects, large concrete infrastructure such as dams. So there's a few different kinds of Portland cement blends, and these are important because you know what, pozzolan is just not available in Kurdistan. The only place I know in the region where they used Portland pozzolan cement is in the Mosul Dam. And they did that because they needed low shrinkage. They needed to make sure that the concrete wouldn't shrink. Now, where did they get the pozzolan from? Well, it's very interesting. Saddam Hussein, he actually purchased New Zealand volcanic ash. So we actually shipped ash to Basra from New Zealand, and it was used in Mosul. So I think that's kind of cool that we made money selling sand to the Arabs. But another way you can make this Portland pozzolan blend is by getting something other than pozzolan, which has this very high alumina silica content, is you could mix it with furnace slag. So what's furnace slag? Well, this is where it's where you make steel. All those factories that make steel and aluminium, that's the waste product. When you're taking iron ore and turning it into steel, the waste product is called furnace slag. And you can mix that with Portland cement too. The other thing you could use is fly ash. What's fly ash? Well, that's actually just ash from coal or charcoal. So when you have a barbecue and at the end of the barbecue you've got ash at the bottom of your barbecue, well, yeah, that could be mixed with Portland cement and you can make it into a very strong concrete, very strong. All of these things have very similar properties. They have very high compressive strengths. They also have quite low shrinkage. One thing you do need to be aware of, though, that for all of them, but particularly with blast furnace slag and fly ash Portland cements, they have very high heat of hydration. So that can be a problem for burning your hands, such as just like lime, but also it can lead to thermal gradient cracking, so we can't use it for things like dams. Now, these are also latent hydraulic cements, meaning that they do not react with water. The pozzolan will not react with water. It must first react with Portland and then it will react with the water. So it's similar to a non-hydraulic cement like lime in that it's a slower reaction because it's a two-step reaction. That means it stays wetter for longer. So that's a good thing. If you were making concrete that was to be used on top of Mount Corrick, and you made the concrete at the concrete factory in Shoresh, well, it then will take you half an hour to drive the concrete truck to the top of Mount Corrick. And if you were just using regular Portland cement, it's already started to go hard and less workable and turn into a thick sludgy honey by the time you reach the top of the mountain. By mixing it with a blend such as blast furnace slag, it's going to be runnier and wetter for longer, making it more workable, more usable. So those are some examples of different blended cements. So this is just what they look like. So on the left you've got slag waste from this is from iron ore and it's from steel or aluminium smelting. When you make aluminium from aluminium ore or you make steel from iron ore, that's what's left. And you would grind that up into a fine powder and then you would mix it with the Portland cement. And fly ash, as I said, that comes from burning coal. Now, we have a big problem, though, don't we, in Kurdistan, and that's availability. Remember, we talked about the two key elements of choosing a material is availability and compatibility. Kurdistan doesn't have any pozzolan. It doesn't have ash from volcanoes. Likewise, in Kurdistan, we do not have any steel or aluminium smelting. There's no factories making steel or aluminium. We would need to import the slag waste from Turkey or Iran if we were to do this. Likewise, we do not have fly ash from burning coal. We have a tiny amount of fly ash from barbecues, but really where we need to be getting fly ash in big quantities is from power stations that burn coal. We do not have any coal burning power stations in Kurdistan. We make our electricity from burning gas, and there's no waste product other than greenhouse gases with burning methane and petroleum gases. So availability is low. That means that in Kurdistan, if you want to make one of these blended cements for making high strength concrete, you've got to import one of these other cements from another country, which can be expensive. Now, the final thing I want to talk to you about is the fineness of the cement particles. Remember what I said, that basically when you're manufacturing the cements, regardless of what the cement is, if it's a Portland cement, a blended cement, or lime or gypsum, you will be putting the cement through a grinder to make sure that the particles are very fine. Now, you need to make sure that it's fine enough that it will have a good surface area so that it will react with the water at a good speed. If it's too fine, it will react too quickly. In fact, it will start bubbling. It might even explode if it's really fine. And if it's too coarse, then the molecules inside those dust particles will not have any contact with the water and they won't react. And so you will end up with a very weak cement. So basically, for nearly all cements, you want it to be smaller, or you want it to be about the size of 75 microns or micrometers. So it needs to be about that size, so fairly small. And so it's a fine dust, similar to flour. And if you have that amount of fineness, you're going to have about the right reaction rate with water. So that's just something to keep in mind as well with cement. Now, that's the end of cement. If you want to have any supplementary reading which talks about cement, read pages 79 to 94 from Shan Somayaji's Civil Engineering Materials. Again, this is available on Kindle. You do not need to buy the book if you don't want to. This is just supplementary reading. Everything you need to know for the assignments and the exam, they've been covered in the lecture. But this is supplementary reading if you want to read about cements in a little bit more depth. So next week we will be talking a little bit about concrete. So some of the things that we've mentioned today, such as hardness and shrinkage and thermal gradient cracking, they're going to become clearer when we go into concrete. But all the other things, they're what you need to know for covering the cement assignment, which will be made available on Moodle. Thank you and goodbye.